Hello, I'm Dr. Richard Branham. I'm at the University of Alabama working on this low temperature plasma project here in the state of Alabama. I'm going to talk to you today about plasma propulsion. The topics that I'm going to cover are what is plasma propulsion, why we would want to use plasma for a propulsion system, the state of the art. I would like to introduce you to the state of the art in those current systems, and then in the discussion with the future path that we are on currently for space travel and how plasma propulsion is going to help us with that. So what is plasma propulsion? Plasma propulsion is a way for us to get beyond the bonds of what chemical systems do for us. You have to ionize the propellant some way and then accelerate it at the back end using electric forces rather than chemical forces and high pressure. The pictures you're looking at here, the deep space concept where they're going to go beyond the solar system. And the only way for us to really be able to do that in a timely manner is with some sort of plasma system. And the one on the right is the J2 thruster that NASA is currently using in orbit on some of the spacecraft that we have in orbit around the Earth. So the thrust on a spacecraft comes from mass that we throw out the back end, ejected, the exhaust. And the amount of mass that we need to throw out the back end, it is inversely proportional to how fast we can throw it out, the exhaust velocity. The faster we can throw it out, the less propellant we need to be able to do what we're trying to do, get to space or get to Mars or change our orbit around around Earth. The spacecraft velocity is also limited by that exhaust velocity. We can't go much faster than what that exhaust velocity out the back end of our thruster is producing. So if we want to get to Mars in any timely manner, we need to have a much higher exhaust velocity on our thrusters. So currently, Mars trip times are about 9 months with current technology, chemical systems. We've sent several payloads out there now, and we can send some robotic missions, but they're somewhat limited. They're not manned missions. Manned missions to Mars are currently not possible, but they will be if we have a much more efficient type propulsion system in the future, and plasma is one of those that can do that. So why would I want to use plasma propulsions then? The propellant that we use for these propulsion systems that we throw out the back can only produce so much thrust. The faster we throw it out, the more efficiently we use it. It's kind of like a miles per gallon. When we use what we call a specific impulse to characterize how fast that propellant comes out the back end. So I will be able to use the propellant much more efficiently if I'm throwing it out much faster. Chemical systems are limited by combustion temperature. So they can get up to about 2,500 to 3,500 Kelvin. They then thermodynamically accelerate that to supersonic, and they can reach 2,500 to 4,500 meters per second in the exhaust, which is pretty good. And we use that to get us on orbit with our launch vehicles. Plasma propulsion, though, isn't limited like the chemical systems are. We can produce plasma at temperatures well above 10,000 degrees Kelvin. And the thrust and propellant utilization then is much better at the higher temperatures and the higher exhaust velocities that we're able to achieve. The plasma is accelerated directly by the electromagnetic force. The chemical systems use high pressure and a high temperature to be able to produce the thrust that they produce. The electric systems can use an applied electric field and magnetic fields to focus and accelerate the plasma to much higher velocities. Conventional exhaust is about 3,000 meters per second. That's our chemical systems. And our plasma propulsion systems are at least an order of magnitude more than that. The state of the art of these electric propulsion systems are the ion thruster and the Hall effect thruster. These thrusters have been researched fairly extensively, and we have both kinds of thrusters on orbit, maintaining satellite orbits for us. The plasma propulsion currently limited, though, by how much plasma we can produce at a given moment. They're ideal for spacecraft because of the limited capability of producing a lot of plasma. That limit on being able to produce a lot of plasma limits how much thrust that we can actually get from these propulsion devices. The exhaust, though, is somewhere between 15,000 and 30,000 meters per second. Not yet able to reach Mars because of that thrust limit, but we're starting to work on that. Current thrust levels achieved are somewhere around 1/1000th to about 5 newtons, or about 1/2000th to about 10 pounds of force. The other part of the electric propulsion system is how much power we can put on board. Everything's going electric now. And something like these electric thrusters are in the hundreds of thousands of watts currently. To produce 1 Newton of thrust, about 2 pounds force, I would need about 20,000 watts of power on orbit. Spacecraft power or don't typically have that much power. At most, the current spacecraft on orbit have about 30,000 watts of power, and that's the communication satellite. So most of that power goes to the communication system, not the propulsion system. The highest propulsion power plasma thruster on orbit currently is about 4,500 watts. So with these limits that we know, we want to be able to take them to the next step. The future of space travel can definitely benefit from the plasma thrusters that we're going to be able to that we're researching and we're going to develop in the near term. The thruster you're looking at here is the high-powered electric thruster where they've taken a concentric thruster. This is a model of a Hall effect thruster. It's a concentric type thruster and has an electric field in the center and a magnetic field around it. And the magnetic field is used to focus and accelerate the plasma. The design that you're looking at there has a concentric, several different channels, concentric design to be able to get up to those much, much higher levels. This guy is full size and it's about 200 watts. The one in the figure can use up to, has demonstrated using up to 100,000 watts and produced thrust on the order of about 5 newtons, about 10 pounds force. We are going to need quite a bit more than that if we go to this kind of design, also currently under development. The VASIMR, the Variable Specific Impulse Magnetoplasma rocket, is trying to produce thrust using 200,000 watts of power. And they're achieving thrust levels of greater than 5 newtons, much greater than the concentric Hall thruster too. But the VASIMR design has the potential, the ability to use 10 megawatt type power supplies. That would be the level that we would need to take a spacecraft to Mars, 10 megawatts. So why do we need plasma propulsion? How are chemical systems limited? What advanced are still needed for plasma propulsion to be useful for interplanetary travel? The following presentation will be between Earth and space, the ionosphere and the magnetosphere. Thank you for your time.
Hi, my name is Plasmy and thank you for watching this video. Make sure to follow us on our social media at CPU2AL on Facebook, LinkedIn, and Instagram. Bye!